A life like a movie, family and childhood. Stephen Hawking was born on January 8, 1942, in Oxford to Frank and Isabel Eileen. He had 3 siblings. Due to their close age difference, he and his sister Mary did not always get along, leading to constant tension. However, as they grew older, this tension faded. Mary later became a successful doctor. Stephen had a better relationship with his other sister, Philippa. His brother Edward, who was adopted when Stephen was 14, had little impact on his early childhood. Unlike the other 3 children, Edward struggled with academics and intellectual pursuits. He was a difficult child and sadly passed away in 2004 for reasons that remain uncertain. If you're wondering what Stephen Hawking was like as a child, he was energetic and healthy. When he was 2.5 years old, his parents decided to enroll him in the nursery at Bryan House School in Highgate. However, Stephen was not ready and tried to express his reluctance by crying loudly. What else could he have done? He was just a small child, overwhelmed by the presence of unfamiliar people. His parents were shocked because all child development books stated that children were ready for social interaction at the age of 2. But clearly, little Stephen was an exception. As a result, they withdrew him from school and did not re-enroll him for another 1.5 years. The educators at Bryan House followed a rigid, memorization-based education system, adhering strictly to a standardized curriculum. Like many geniuses, Stephen found this system frustrating and refused to conform. Perhaps because of this, he only learned to read and write at the age of 8. Growing up during wartime, Stephen had a deep fascination with model trains. However, toys were hard to come by. Noticing this, his father crafted a wooden train for him. But Stephen wanted more. He wanted his train to move on its own. His father eventually found a broken wind-up train, repaired it, and gave it to him as a Christmas present. Unfortunately, it didn't last long. Later, after returning from a trip to America, his father brought him an American train. While Stephen was thrilled, he was more curious about electric trains than wind-up ones. Eventually, he saved up enough money to buy an electric train, but its motor had issues. Though he had it repaired, it never worked perfectly. Why are we telling you this? Because Stephen not only loved playing with trains, ships, and airplane models, but also tried to build them. He was particularly interested in understanding how these objects functioned, their mechanics. This curiosity would one day lead him to explore and uncover the workings of the universe itself. School years. In 1950, due to his father's job change, Stephen moved with his family from Hampstead to the newly built National Institute for Medical Research on the northern edge of London. After a bad experience in the nursery of Bryan House School in Highgate, he attended St Albans Girls' School in their new town. Don't laugh. Although it was primarily a girls' school, it accepted boys up to the age of 10. Stephen attended this school until he turned 10. In the 1950s, the British education system was entirely hierarchical. Students were divided into academic and non-academic groups, and within academic schools, there were A, B, and C classes. Based on his exam results, Stephen qualified for the A division at St Albans School. However, to remain in the A class, he had to pass year-end exams and rank in the top 20. Although this system challenged him, he consistently managed to stay in the A class. At the age of 13, his father wanted him to apply to Westminster, one of Britain's leading private schools. However, since their financial situation was not strong, he could only attend if he won a scholarship. To secure this, he needed to pass an entrance exam. Unfortunately, on the day of the exam, he fell ill and was unable to take it, forcing him to continue his education at St. Albans. Despite having only above-average grades, his friends nicknamed him Einstein. It seems they were quite visionary. At that time, Stephen's father was researching tropical diseases and often took Stephen to his laboratory in Mill Hill. Stephen particularly enjoyed using the microscope in the lab. He was curious about how objects worked, often taking things apart, but struggling to put them back together. His father recognized Stephen's interest in science and always supported him in this regard. In his last 2 years of school, Stephen wanted to focus on and specialize in mathematics and physics. However, his father wanted him to study medicine. Stephen found biology too vague and based on rote learning. His father eventually realized that Stephen wouldn't pursue biology, but he still tried to steer him towards chemistry instead of mathematics. Although Stephen found chemistry interesting and exciting, he ultimately chose physics and astronomy. University years. Stephen's father played a significant role in his education. He wanted his son to study at Oxford or Cambridge, as he himself was an Oxford graduate. At the time, Oxford University did not have a mathematics department, so his father encouraged him to study chemistry instead. Despite his teachers thinking he was too young for Oxford, Stephen took the scholarship exam in March 1959. A few days after returning from Oxford, he received a telegram informing him that he had passed. Thus, in 1959, at the age of 17, Stephen began his university education at Oxford. During his first 2 years, he felt lonely, as most of the other students were older and had already completed their military service. To make more friends, he joined the rowing team in his 3rd year. As a rower, he took on the role of coxswain. However, in his first race, he had a major mishap. He lost grip of the rope he was supposed to hold, causing it to get tangled in the boat, which veered off course and led to their disqualification. This was quite demoralizing. In another race, his team collided with another 8-man boat, but this time, he was not at fault. After these incidents, Stephen left the rowing team. However, that year, he made many friends and expanded his social circle. Despite not being a highly successful team, Stephen worked hard to help them improve. During his 3 years at Oxford, Stephen estimated that he studied for about 1,000 hours. As his final exams approached, he felt unprepared and decided to answer only theoretical physics questions instead of those requiring detailed knowledge. However, since he had stayed up all night before the exam, he did not perform well. His results were on the borderline between 1st and 2nd class honors, so he had to undergo an interview with Oxford examiners. When asked about his future plans, he responded, "I want to do research. If you award me a 1st-class degree, I will go to Cambridge. If you give me a 2nd-class degree, I will stay at Oxford." In the end, he graduated with 1st-class honors. Postgraduate years. At that time, Oxford did not offer cosmology studies. Wanting to specialize in cosmology, Stephen went to Cambridge and began his postgraduate studies there in October 1962. He wanted to work with Fred Hoyle, the most prominent astronomer of the time and a staunch defender of the steady-state theory. However, because Hoyle had too many students, Stephen was instead assigned to Dennis Sciama, whom he had never met or even heard of before. Initially disappointed, he soon realized that despite their differing views on many topics, Sciama was always accessible and played a crucial role in his academic development. A sudden turn, Stephen Hawking's diagnosis. Suddenly, an unfortunate health issue arose. Stephen Hawking suffered from a rare, early onset and slow-progressing form of amyotrophic lateral sclerosis, ALS. Doctors diagnosed him with motor neuron disease. The diagnosis was made in 1963 when Hawking was just 21 years old, and doctors gave him only 2 years to live. This disease paralyzed the nervous system by gradually killing 80% of motor neurons, yet it did not affect the brain's cognitive functions. After being diagnosed with motor neuron disease, Stephen fell into depression. Despite doctors advising him to continue his studies, he saw no point in doing so. However, the disease progressed more slowly than expected. Although he struggled to walk without support, and his speech became nearly incomprehensible over time, it became clear that the doctor's initial prognosis of only 2 years was incorrect. Stephen had a great deal of work to do, and with encouragement from his university professor, he returned to scientific research. His professor, Dennis Sciama, recommended that Hawking study astrophysics. However, Stephen disagreed. He had come to Cambridge to research cosmology, and he was determined to pursue it, the path to scientific discovery. Following this decision, Stephen read older books on general relativity and attended Sciama's lectures at London's King's College every week. He could follow the words and equations, but struggled to grasp the subject. During this period, he was introduced to Wheeler-Feynman electrodynamics. According to this theory, electricity and magnetism are symmetric in the dimension of time. While this theory was possible in a steady-state universe where matter density remained constant, it was not applicable in a Big Bang universe where density decreased as the universe expanded. Around the same time, 2 astrophysicists, Hoyle and Narlikar, worked on Wheeler-Feynman electrodynamics in expanding universes, developing a new gravitational theory that was symmetric in time. They presented this theory in 1964 at the Royal Society's Conference on Natural Sciences. Stephen attended the conference and, during the Q&A session, challenged their work by arguing that the effect of all matter in a steady-state universe would render masses infinite. Hoyle asked why he made such a claim, to which Stephen responded that he had calculated it. Although most thought he had calculated it on the spot, he had actually seen the draft of the paper beforehand and had done the necessary computations. Hoyle was furious and suspected that Stephen had been sent to sabotage the conference. However, later on, Hoyle accepted Stephen into his institute. A new purpose, love, and determination. Following his ALS diagnosis, Stephen became engaged to Jane Wilde. This relationship greatly improved his mental well-being. Now, he had something worth living for. However, to marry Jane, he needed a job, and to secure a job, he first had to complete his doctorate. To support himself during his PhD, he applied for a research grant at one of Cambridge University's faculties and won it. Thanks to this grant, he and Jane married on July 14, 1965. Their first child, Robert, was born in the 2nd year of their marriage. Their second child, Lucy, was born 3 years later, and their third child, Timothy, was born in the 9th year of their marriage. Groundbreaking work in cosmology. When Stephen began his doctoral studies, the scientific community was engaged in heated debates about theories regarding the universe's origin. The primary competing theories were the Big Bang and the steady-state models. Inspired by Roger Penrose's theorem on space-time singularities at the center of black holes, Hawking applied the same concept to the entire universe. He studied the fundamental principles of the universe and, alongside Penrose, demonstrated that Einstein's general theory of relativity governing space and time led from the Big Bang to black holes. This conclusion revealed the necessity of merging quantum mechanics with general relativity. It was one of the greatest discoveries of the second half of the 20th century. One outcome of this unification was the revelation that black holes were not entirely black. Instead, they emitted radiation, evaporated, and eventually disappeared. Another implication was that the universe had a definitive beginning and a boundary. This meant that the universe's origin followed scientific principles. In 1965, Hawking wrote his thesis on this subject, which was approved in 1966. In March 1966, he earned his PhD in applied mathematics and theoretical physics, specializing in general relativity and cosmology. Due to his groundbreaking work, he was awarded the prestigious Adams Prize that year. Black holes and revolutionary discoveries. Stephen initially expanded the concept of singularity theorems, exploring not only the existence of singularities, but also the possibility that the universe itself began as a singularity. The papers he co-authored with his colleague earned second place in the 1968 Gravity Research Foundation competition. In 1970, he published evidence that if the universe adhered to the laws of general relativity and followed any of Alexander Friedman's physical cosmology models, it must have originated as a singularity. For his contributions, Hawking was awarded a specially designated Fellowship for Discrimination in Science. Meanwhile, in 1970, just days after the birth of his daughter Lucy, Stephen experienced a sudden insight and began working on black holes. What triggered this revelation? Genius minds often work in such ways. Ideas arrive unexpectedly. One night, just before going to bed, Stephen realized that the causal structure theory he had developed for singularity theorems could be applied to black holes. Specifically, he noticed that the event horizon, the boundary of a black hole, would always expand. If two black holes collided and merged, the surface area of the resulting black hole would be larger than the sum of the two original ones. This discovery, along with additional properties identified by Stephen, Jim Bardeen, and Brandon Carter, suggested that surface area behaved like a black hole's entropy. However, surface area alone could not be entropy, because if black holes had entropy, they would also have temperature, and a hot mass should radiate energy. Yet conventional wisdom held that black holes were dark and emitted nothing. This period of exciting discoveries culminated in the 1972 Larouche Summer School, where they solved many challenging problems in black hole theory. One particularly significant breakthrough came when David Robinson and Stephen proved the no-hair theorem, which suggested that a black hole could be characterized solely by two properties: its mass and its rotation. This implied that a black hole had entropy because multiple collapsing stars could form a black hole with the same mass and rotation. Hawking's work revolutionized our understanding of the universe and solidified his legacy as one of the greatest scientific minds in history. In January 1971, his paper titled Black Holes won the Gravity Research Foundation Award. Meanwhile, his first book, The Large-Scale Structure of Space-Time, co-written with George Ellis, was published in 1973. Starting in 1973, Stephen began studying quantum gravity and quantum mechanics. The results he presented in 1974 showed that black holes emit radiation, now known as Hawking radiation, which continues until they deplete their energy and evaporate. Initially, Hawking radiation was a controversial topic. However, by the late 1970s, as more research was published, this discovery was recognized as a major breakthrough in theoretical physics. Just weeks after explaining Hawking radiation, Stephen was elected a Fellow of the Royal Society (FRS) in 1974. He also made a scientific bet with a colleague regarding whether the X-ray source, Cygnus X1, was a black hole. In 1990, Stephen admitted that he had lost the bet. This was the first of several wagers he made with Thorne and others. In 1975, Stephen Hawking returned to Cambridge for a more academic position. The 1970s saw an increasing public interest in black holes and the physicists studying them. During this period, Stephen gave frequent interviews for print media and television, which helped boost the academic recognition of his work. In 1975, he was awarded both the Eddington Medal and the Pius XI Gold Medal. In 1976, he received the Danny Heinemann Prize, the Maxwell Medal and Prize, and the Hughes Medal. By 1977, he had been appointed Professor of Gravitational Physics. The following year, he received the Albert Einstein Medal and an honorary doctorate from Oxford University. In 1979, their third child, Tim, was born. This intensified Jane's emotional struggles. She believed Stephen would not live much longer and wanted someone who could support her and the children after his passing. She found Jonathan Jones, a musician who played the organ at a nearby church, and gave him a room in their home. Stephen initially objected to this arrangement, but ultimately agreed, realizing that someone would need to care for the children after his death. Despite these difficult times, Stephen never stopped thinking and trying to understand the universe. In 1979, he was appointed Lucasian Professor of Mathematics at Cambridge University. In 1981, he proposed that when a black hole evaporates, the information within it is irreversibly lost. This information paradox violated a fundamental principle of quantum mechanics and led to years of debate, including the Black Hole War, involving Leonard Susskind and Gerard 't Hooft. In the early 1980s, Alan Guth proposed the theory of cosmic inflation. This theory suggested that following the Big Bang, the universe initially expanded at an incredible speed before transitioning to a slower rate of expansion. After a conference in Moscow in October 1981, a 3-week workshop on the very early universe was held at Cambridge University in the summer of 1982, focusing primarily on inflation theory. Stephen Hawking launched new quantum research into the origins of the universe. In 1981, at a conference in the Vatican, he presented a study suggesting that the universe might have no boundary, beginning, or end. He developed this research in collaboration with Jim Hartley, and in 1983, they published a model known as the Hartle-Hawking state. This model suggested that before the Planck era, the universe had no boundary in space-time. Time did not exist before the Big Bang, making the concept of a beginning meaningless. During this time, Stephen's illness continued to worsen. One symptom was prolonged coughing fits caused by food getting stuck in his throat. In 1985, during a visit to CERN in Switzerland, Stephen developed pneumonia. He was admitted to a cantonal hospital and placed on a ventilator. Doctors there had little hope for his recovery and suggested to Jane that they disconnect life support. Jane refused and arranged for Stephen to be transported by air ambulance to Addenbrooke's Hospital in Cambridge. Despite the doctor's efforts, they eventually had to perform a tracheostomy. To clarify, a tracheostomy is a medical procedure where an external hole is made below the larynx to create a new airway. However, after the tracheostomy, Stephen lost his ability to speak entirely. His only means of communication was by raising and lowering his eyebrows while someone pointed to letters, spelling out words. Writing a scientific paper, let alone having a simple conversation, became incredibly challenging. Then, a computer specialist in California named Walt Woltosz learned of Stephen's struggles and sent him a computer program called Equalizer. Starting in 1986, Stephen used a computer mounted on his wheelchair that converted text to speech, allowing him to communicate. With support from his family and colleagues, he continued both his scientific work and daily life. By squeezing an electronic switch in his hand, he could select words displayed on his screen at an average rate of 10 words per minute. This way, he could type any word he wanted to say. His computer's memory contained around 2,600 words, the same number an average person regularly uses, so he did not struggle to express his thoughts. Additionally, he could navigate through on-screen word menus using a switch in his hand, which made communication easier. Still, after leaving the hospital, he faced greater challenges as he required constant care. Stephen initially thought his scientific career had come to an end. However, with the help of the LaTeX program, which allowed him to write mathematical equations using normal characters, he resumed his work. This was a major turning point, allowing him to continue his career in science. During this period, he continued to receive honorary awards. In 1981, he was awarded the American Franklin Medal. In the 1982 New Year's Honors, he was appointed a Commander of the Order of the British Empire, CBE. Although these honors did not significantly change his financial situation, they motivated him to provide for his children's education and household expenses. In 1982, Stephen had the idea to write a popular book about the universe. One motivation was to help pay for his daughter's school tuition, but his primary goal was to show how far our understanding of the universe had progressed and that we might be close to discovering a complete theory explaining everything within it. If he was going to write a book, he wanted it to reach as many people as possible. The first draft was submitted to publishers in 1984 through his literary agent. However, publishers found it too technical and asked him to make it more accessible to non-scientists. Stephen revised the book repeatedly, responding to publishers' objections and requests for clarification. At times, he felt it would never be finished, but he understood the publishers' concerns. Finally, the book was published on April 1, 1988, and quickly became a bestseller, making it onto the New York Times bestsellers list. It remained on the London Times bestsellers list for over 100 weeks and was translated into 40 languages worldwide. After the publication of his book, the media's interest in Stephen grew even more. Newsweek magazine featured him on its cover, and a television program described him as the master of the universe. Due to his work, Stephen Hawking traveled frequently. His difficulty in refusing invitations and visitors left him with little time for his research and students. Yet he continued to receive awards. He earned 5 more honorary degrees, further enhancing his academic recognition. These included the Royal Astronomical Society Gold Medal, 1985, the Paul Dirac Medal, 1987, and along with Penrose, the prestigious Wolf Prize, 1988. However, by the late 1990s, he declined knighthood in protest of the UK's science funding policies. Despite all these achievements, his marriage was not going well. His wife Jane's growing closeness with Jonathan made Stephen unhappy. Unable to bear the situation any longer, Stephen left home in 1990 and began living with his nurse, Elaine Mason. In 1995, Stephen married Elaine. Their marriage was both passionate and turbulent, with good days and bad. Elaine's nursing skills saved Stephen's life multiple times. After his tracheostomy, a plastic tube secured with an inflatable cuff was inserted to prevent food and saliva from entering his lungs. Over time, this cuff damaged his windpipe. leading to coughing fits and blockages. While returning from a conference in Crete, Stephen began coughing on the plane. A surgeon, David Howard, who was on the same flight, approached Elaine and offered to help. He proposed a laryngectomy, which would completely separate Stephen's windpipe from his throat, eliminating the need for a cuffed tube. Despite doctors at Addenbrooke's hospital calling it too risky, Elaine insisted, and the surgery was performed at another hospital in London. This operation saved Stephen's life. If they had waited just 2 more weeks, a hole would have formed between his windpipe and throat, causing his lungs to fill with blood. Having endured incredibly difficult times, constantly teetering between life and death, Stephen never gave up on life or science. In 1993, he co-edited a book on Euclidean quantum gravity with Gary Gibbons and published a collection of his papers on black holes and the Big Bang. In 1994, at Cambridge's Newton Institute, he and Roger Penrose delivered a series of 6 lectures, later published in 1996 as The Nature of Space and Time. In addition to continuing his scientific work, Stephen also maintained a strong public presence, making science accessible to a wider audience. The film adaptation of A Brief History of Time, directed by Errol Morris and produced by Steven Spielberg, was released in 1992. Stephen initially wanted the film to be scientific rather than biographical, but he was convinced otherwise. In 1993, he published Black Holes and Baby Universes and Other Essays, a collection of popular articles, interviews, and lectures. In 1997, a 6-part TV series, Stephen Hawking's Universe, was released alongside a book. This time, as Stephen insisted, the focus was entirely on science. Final years, 2000 to 2018. In 2001, Stephen continued simplifying science for a general audience with the release of The Universe in a Nutshell. In 2005, he co-authored A Briefer History of Time with Leonard Mlodinow, further refining his explanations of complex physics. He also collaborated with his daughter on a book project. In 2007, they published George's Secret Key to the Universe, a children's book designed to explain theoretical physics in an accessible way, featuring characters inspired by the Hawking family. Several sequels followed. During this period, Stephen faced increasing health crises, which took a heavy emotional toll on Elaine. Eventually, the couple divorced in 2007. From then until his passing, Stephen lived with his caregiver. Stephen traveled extensively, visiting Chile, Easter Island, South Africa, Spain, Canada, and the United States. Due to his disability, he traveled by private jet, which became his only means of international travel until 2011. In 2003, physicists agreed that Stephen was wrong about information loss in black holes. In 2004, at a conference in Dublin, he admitted losing his 1997 bet with John Preskill and presented his own, somewhat controversial, solution to the black hole information paradox. His 2005 paper argued that information loss could be explained by considering the alternative histories of the universe. However, in January 2014, Stephen called his belief in black hole information loss "my biggest blunder." Another bet Stephen lost involved the Higgs boson. He had long argued that it would never be found. The particle was proposed in 1964 by Peter Higgs as part of the Higgs field theory. Stephen and Higgs engaged in heated debates in 2002 and 2008, with Higgs criticizing Stephen's fame for giving him undue credibility. However, in July 2012, the Higgs boson was discovered at CERN's Large Hadron Collider. Stephen admitted defeat and acknowledged that Higgs deserved the 2013 Nobel Prize in Physics. Throughout his career, Stephen supervised 39 successful PhD students, with only one failing to complete their doctorate. In 2009, he retired as Lucasian Professor of Mathematics at Cambridge due to university policy. Despite suggesting that he might leave the UK in protest against funding cuts to basic scientific research, he continued as the Director of Research at Cambridge's Department of Applied Mathematics and Theoretical Physics. In August 2015, he proposed that information might not be completely lost in black holes and suggested a way to retrieve it. In July 2017, Imperial College London awarded him an honorary doctorate. On March 14, 2018, at the age of 76, Stephen Hawking passed away peacefully at his home in Cambridge. His final paper, Soft Hair on Black Holes, was published posthumously in the Journal of High Energy Physics on April 27, 2018. Stephen Hawking had an incredibly difficult life, yet he never stopped working and fighting. It's impossible not to admire him. His story is a source of inspiration in many ways. Despite being one of the greatest geniuses of the century, Stephen struggled to learn to read until he was 8 years old and was known as a lazy student at Oxford. Yet, his accomplishments speak for themselves. Isn't that truly inspiring? Interestingly, Stephen Hawking was born on the anniversary of Galileo's death and died on Albert Einstein's birthday. Was it just a coincidence or a miracle? The Big Bang and Singularity. At the moment of the Big Bang, the universe was an infinitely dense object compressed into an infinitely small point. After the Big Bang, it rapidly expanded to reach its current size, approximately a sphere with a diameter of 90 billion light-years, and it continues to expand today. This state, where matter is compressed into an infinitely small point with infinite density, is called a singularity. According to Einstein's theory of relativity, gravity also reaches infinity in this condition, and this is precisely where the problem begins. Einstein's relativity theory fails in this context, forcing us to accept that the universe spontaneously emerged from nothingness and that the laws of physics formed alongside it. Before Hawking, physicists attempted to resolve this paradox through eternal universe cycle theories, which proposed a series of eternal universes. Each universe would be born through a Big Bang, expand, and then cease expanding due to the gravitational pull of its own matter. However, Hawking demonstrated that the universe did not necessarily have to form from the remnants of a preceding universe. In the 1970s, he introduced a groundbreaking idea in his paper, Singularities in Gravitational Collapse and Cosmology, co-authored with Roger Penrose. According to their findings, quantum fluctuations in the void before the universe could have caused its spontaneous emergence. Hawking's extraordinary genius began to shine at this point. He had just graduated from Oxford and had many subjects to master in mathematics. At the same time, he had just been diagnosed with ALS, a disease that would eventually leave him completely paralyzed. Under the guidance of Siyama, Hawking started contemplating the Big Bang theory. While the theory is widely accepted today, it was still debated at the time. He realized that the Big Bang was essentially the reverse of a black hole's collapse. He refined this idea with Penrose, and in 1970, they published a paper explaining that general relativity indicated the universe began as a singularity. During this period, Hawking's disease progressed, making it difficult for him to walk, even with crutches. By the late 1970s, one night, as he struggled to get into bed, he had a sudden revelation that led to a series of discoveries explaining black holes' behavior. He realized that a black hole's size could only increase. It could never shrink. Since nothing approaching it could escape, black holes could only accumulate more matter, thus growing in mass. This meant that a black hole's mass determined its size, which in turn defined the event horizon's radius, the boundary beyond which nothing could escape. Like an inflating balloon, this boundary would expand uncontrollably outward. Hawking took this idea even further, arguing that even in the case of two black holes colliding, they would never break into smaller pieces. He also made another groundbreaking observation. The event horizon's ever-expanding nature could be compared to a dimension in physics that could only increase: entropy. In physics, entropy measures the disorder in a system. Atoms in a crystal have low entropy, whereas atoms moving freely in a gas have high entropy. According to quantum theory, empty space is never truly empty, because space cannot be entirely flat and void. Instead, it is teeming with activity. Pairs of particles constantly appear spontaneously, one forming matter, the other antimatter. Since one has positive energy and the other negative energy, no new net energy is created. These pairs annihilate each other almost instantly, making them undetectable, hence the term virtual particles. Hawking proposed that if these particle pairs formed near a black hole, they could transition from virtual to real. Space-time and gravity. Stephen Hawking clarified the idea that space and time originated with the Big Bang. If we rewind the universe like a film, back to the singularity of the Big Bang, space would replace time, and ultimately, space-time itself, the fabric of the universe, would lose its meaning entirely. The same thing happens to an object falling into a black hole. First, space compresses into a single-dimensional line directed into the black hole. Then, time replaces three-dimensional space, and every point in time converges at the singularity at the black hole's center. We are all constantly traveling through time, moving from the past to the future as we age. However, Stephen Hawking demonstrated that traveling to the past is impossible. This cannot be considered absolute physical proof, as theoretical wormholes might allow for time travel. Partial singularity. Imagine that, at the moment of the Big Bang, the universe was not an infinitely dense, infinitely small, infinitely hot, and infinitely gravitational point, but rather a small yet finite-sized point. This point was too small for the physical laws governing our universe to function, yet large enough for quantum field theory, the foundation of all possible universe's physical laws, to persist. In this case, absolute nothingness, void, would not have preceded the universe. Instead, we must accept the existence of a virtual space composed of virtual particles, even if it was not real space. To address the age-old question of whether the chicken or the egg came first, Stephen Hawking formulated quantum fluctuations and demonstrated that the Big Bang could have spontaneously emerged in this virtual particle space. Cosmic microwave background radiation. Stephen Hawking also predicted secondary quantum fluctuations, energy fluctuations that arose uniquely within our universe immediately after the Big Bang. Later, physicist Alan Guth demonstrated that right after its formation, the universe inflated at a rate trillions of times faster than the speed of light. As a result, the matter and energy created by quantum fluctuations were evenly distributed across the universe on a large scale. However, on a smaller scale, matter clumped in certain areas while leaving other areas as empty space. This is why, when we look a billion light-years into space, we see trillions of galaxies in every direction. On average, their distribution appears uniform, and the universe contains between 2 to 10 trillion galaxies. Meanwhile, within our galaxy, there are planets, stars, and vast empty spaces containing only sparse gas atoms. In short, Stephen Hawking explained how quantum fluctuations both created the universe from emptiness and shaped its expansion and transformation into what we observe today. The brilliant mind that illuminated us. Stephen Hawking, who passed away at 76, not only revolutionized science, but also left us with profound words of wisdom. Despite losing his ability to speak due to his illness, he continued to share his insights through a voice synthesizer. Let's take a moment to listen to his words. Regarding the question of why the universe exists, Hawking said, "If we find the answer to that, it would be the ultimate triumph of human reason. For then, we would truly know the mind of God." A Brief History of Time, 1988. On commercial success, I want my books to be sold in airport bookstores. New York Times interview, 2004. On fame. The downside of my fame is that I cannot go anywhere in the world without being recognized, wearing dark sunglasses and a wig.